Every Bitcoin transaction carries a hidden clock. Every block begins with a transaction that creates money from nothing. The network deliberately charges less for some bytes than others. These aren't bugs. There's three carefully designed rules in Bitcoin's protocol. We'll crack open a raw transaction and examine lock time, Coinbase transactions, and transaction weight, three mechanisms that control when transactions confirm, how new coins enter circulation, and why some data costs less in a block. Let's start with lock time. Lock time is a 4-byte unsigned integer at the very end of every serialized transaction. It restricts the earliest point at which that transaction may appear in a block. The simplest case, a lock time of 0 means no restriction, include this transaction anytime. Most transactions use 0. But a non-zero lock time has a dual interpretation controlled by a single threshold, 500 million. Below that threshold, the network reads the value as a block height. At or above 500 million, it's interpreted as epoch time, second since January 1st, 1970. Here's the dual interpretation in practice. A lock time of 123,456 means this transaction cannot appear before block 123,456. A lock time of 1.7 billion falls in the epoch time zone. A Unix timestamp, roughly November 2023. The network checks lock time against median time passed, the median of the previous 11 block timestamps, not the wall clock. This trails real time by 1 to 2 hours. This was Bitcoin's earliest known soft fork, activated around block 31,000. Lock time controls when a transaction can confirm. But what about the very first transaction in every block? The one that creates new Bitcoin? This is the Coinbase transaction, and it's structurally unique. Let's compare. A normal transaction input references a previous output using an outpoint, that's a transaction ID plus an output index. It also includes a signature script to prove authorization. Now look at the Coinbase input. Its transaction ID is 32 bytes of zeros, a null outpoint. The index is set to its maximum value, all Fs in hexadecimal or 0xFFFFFF. And instead of a signature script, it contains a free-form Coinbase data field between 2 and 100 bytes long. Miners use this space for the block height, extra nonce for mining, and sometimes even vanity messages. One more thing. Since segregated witness, the Coinbase must also include a witness commitment output. The Coinbase outputs are capped. The total output value cannot exceed the block subsidy plus all transaction fees collected in that block. The subsidy itself follows a precise halving schedule defined by the formula subsidy equals the floor of 50 times 10 to the 8th divided by 2 raised to the power of the floor of height divided by 210,000, all measured in satoshis. Let's walk through each halving error. Halving 0 covers block 0 through 209,999 with a subsidy of 50 BTC. At halving 1, starting at block 210,000 through 419,999, the subsidy drops to 25 BTC. Halving 2 covers blocks 420,000 through 629,999 at 12.5 BTC. Halving 3 spans blocks 630,000 through 839,999 at 6.25 BTC. And halving 4, the most recent, covers blocks 840,000 through 1,049,999, bringing the subsidy down to 3.125 BTC. This pattern repeats every 210,000 blocks. The key constraint is that total Coinbase outputs must be less than or equal to fees plus subsidy. Now, one critical rule, Coinbase outputs require 100 confirmations before they can be spent, and this is called the maturity requirement. If a block gets reorganized out of the chain, its Coinbase outputs simply vanish because they were created from nothing. The 100-block maturity window prevents downstream transactions from being invalidated by such reorganizations. Eventually, around halving 33, the subsidy reaches 0 satoshis and no new Bitcoin will be created. We now know how transactions are timed and how new coins enter, but there's a limit to what fits in each block, and Bitcoin's measurement of that limit is deliberately asymmetric. Bitcoin uses a unit called weight. Each byte in a serialized transaction is multiplied by a weight factor, 4 or 1, depending on where it sits. Non-witness data, version, inputs, outputs, and log time carries a factor of 4. Witness data, the segue marker, flag, and witness fields carries a factor of just 1. A block's maximum capacity is 4 million weight units. To convert weight to virtual bytes, you simply divide by 4. Fee rates are then quoted in satoshis per virtual byte. Here's the complete breakdown. Factor 4 applies to version, inputs count, outpoint, input script length, sequence number, outputs count, amount, output script, and log time. Factor 1 applies to the segue marker byte, the flag byte, witness item count, and the witness items themselves. Every field falls into one of these two categories. The asymmetry is the key design feature. Witness data is discounted by a factor of 4 relative to everything else. Remember, 4 weight units equal 1 virtual byte. Let's walk through a concrete example, a single input to output transaction from Alice to Bob. We'll build a table showing each field, its size in bytes, the weight factor, and the resulting weight units. First, version, 4 bytes times a factor of 4 equals 16 weight units. Next, the marker field, 1 byte times a factor of 1 equals just 1 weight unit. This is a witness field, so it gets the discount. Flag, also 1 byte times 1 equals 1 weight unit. Another witness field. Input count, 1 byte times 4 equals 4 weight units. The outpoint, which identifies the coin being spent, 36 bytes times 4 equals 144 weight units. Input script length, 1 byte times 4 equals 4. Sequence, 4 bytes times 4 equals 16. Output count, 1 byte times 4 equals 4. Amounts for our two outputs, 16 bytes total times 4 equals 64 weight units. Output scripts, 58 bytes times 4 equals 232 weight units. Now the witness data. Witness count. 1 byte times a factor of 1 equals just 1 weight unit. Witness items containing the signature and public key, 66 bytes times 1 equals 66 weight units. Notice the big discount here. At factor 4, this would have been 264. Finally, log time. 4 bytes times 4 equals 16. Now sum everything up. 16 plus 1 plus 1 plus 4 plus 144 plus 4 plus 16 plus 4 plus 64 plus 232 plus 1 plus 66 plus 16 gives us 569 weight units total. Divide by 4 to convert to virtual bytes. 569 divided by 4 equals 142.25 virtual bytes. Now visualize this. The raw transaction totals about 190 bytes. Witness data, the marker, flag, and witness fields accounts for 68 bytes, roughly 35% of the raw size. But in weight, that same data contributes only 69 of 569 weight units, about 12%. Same bytes, different cost. This is the witness discount in action. Spending a UTXO requires witness data, so the discount makes spending cheaper relative to creating new outputs. These three mechanisms form an interconnected design. Lock time gives Bitcoin time-restricted validity. A transaction declares the earliest moment it's eligible for confirmation, measured in blocks or epoch seconds. Coinbase transactions govern money creation under strict accounting. Outputs cannot exceed fees plus subsidy. and new coins need 100 confirmations before spending. The weight system shapes economic incentives around block space. The witness discount was engineered to reduce the cost of inputs, which destroy UTXOs, relative to outputs, which create them. This fights UTXO set bloat, a real scalability concern since every full node stores the entire UTXO set in memory. Between these three concepts, deep connections emerge. Coinbase outputs carry a 100-block maturity lock. Coinbase outputs count toward the block weight limit, and the lock time field itself costs 16 weight units, 4 bytes times 4. At the heart of it all is a single design philosophy: incentive-aligned protocol rules. And the key insight: the witness discount makes it cheaper to spend UTXOs than to create them, directly fighting UTXO set bloat.